This video is a completion of the lesson that we started yesterday on the finding the volume of the largest volume of the box that we created. So just as a recap of what we did yesterday. Yesterday we started off with a 11 inch. So the length down here was 11 inches by the width was 8.5 inches paper. And what we did was we cut out squares, and we cut out squares that were different sizes. So we cut them out from like 0.5 inches to 4 inches. So I'm going to label each one of these squares X, so I don't know what they are. And we cut those out depending on what group you were in, different widths. And so then what you did was you folded up your box, and then this became your open top box. So if this whole length here was 11, then if I cut out X on this side and X on this side, my new length is now 11 minus 2X. And then the same with the width. If this whole width was 8.5 inches, and I cut out X on this side and X on this side, then my new width is 8.5 minus 2X. And then the height of my box was whatever size of square that we cut out. Okay, so yesterday we created this chart, and hopefully you have this chart still in your notes. And this chart showed the side length of the squares that you cut out, so anywhere from 0.5 inches to 4 inches. It found us our new length and our new width, and we calculated the area of the square base, and we calculated the height, and we calculated the volume of the box. And so you should already have this graphed, this first one graphed in there, but just to kind of remind you here. So each one of these is 1 here. And so I plotted the point 0.5. So I'm plotting this on the X, and I'm plotting the area of the square base on the Y. So my first thing that I did was I plotted, this is 60, 70, 80, 90. So I plotted 0.575, which is about right here, 158.5, 1.544, and these are just approximate points, 231.5, 2.5, 21, 3, 12.5, 3.5, 6, and 4, 1.5. And that's what our graph looked like. And then we also graphed it on Desmos. So the next slide is going to show you the Desmos slide. Okay, so after we plotted those by hand, we put it into Desmos, in this table into Desmos, and make sure you know how to put a table into Desmos. If you were gone yesterday, make sure you ask somebody in class that was here, but there's a little plus sign here in the top left-hand corner of Desmos, and that will allow you to add a table. And so it graphed this graph right here. And so yesterday we talked about that this graph really wasn't linear, and we talked about what it possibly could be. And so what I want you to see is that if I could connect these points with a curve here, that it appears to almost be similar to our quadratic that we've done. And so what I want you to see that on the next slide, I'm going to type in the area function for the area of the base. So in my rectangle, my length was 11 minus 2x, and my width was 8.5 minus 2x. So my area function is going to be the length times the width. So it's going to be 11 minus 2x times 8.5 minus 2x. And I'm actually going to type that into Desmos on the next slide and show you what happens here. All right, so this is the next slide here, and I've actually typed in my area function right here, 11 minus 2x and 8.5 minus 2x into Desmos. And notice what happened here was that curve went through all of my data points. And so it is, since I have two factors, This is a factor, and this is a factor. And anytime we have two factors, we are going to have a quadratic equation. And so even though it doesn't look like our normal parabola looks, it is a quadratic equation. And the reason why it doesn't look like a quadratic equation is because of what I have my domain set at. I have my window here going from a little under 0, so I have from 0 to a little over 4 here on my x-axis, and so I'm not showing the whole entire graph. All right, so let's talk about what you're seeing right here. So I am seeing, if I look at the x-intercept of this graph, and so right here is what I'm focusing on, this point right here. That point right there is 4.25, 0. And so the reason why I am going to limit my domain to be between 0 and 4.25. If you think about this for a little bit, if I had a piece of paper that was 8.5 wide, and I cut it directly in half, so 8.5 divided by 2 is 4.25. I would just have two sheets of paper. I wouldn't have anything to fold up to make a box out of. And I have to cut something out, so I have to have my domain be, my cutout of my squares be greater than 0. So my domain is greater than 0 but less than 4.25, because if I cut out a square that is equal to 4.25, I will just have two sheets of paper and I won't have a box. But I have to cut out a square that's greater than 0, because if I don't cut out a square at all, I won't have a box. I'll just have a sheet of paper. So that's why my domain is that. And so that's why I have my window set like this. If you would take and zoom out of this window, and I don't have a slide of this, but if you do this on Desmos, hit the plus or minus sign and zoom out, you will see the whole entire parabola, and it will look like a quadratic equation that we're used to seeing. Okay, so on the next slide here, what I'm talking about is finding the volume of the box. And so remember, our box here was an open top box, and the length of my box was 11 minus 2x. The width of my box was 8.5 minus 2x, and the height of my box was x. So if volume equals length times width times height, all I'm going to do is I'm going to sub in for that. So volume is equal to 11 minus 2x times 8.5 minus 2x times x. So in this graph right here, I want you to sketch on the x-axis. I want you to do the side length of the squares. So that will be like the 0.5, the 1, the 1.5, etc. And on the y-axis, you're going to sketch the volume. Okay, so I want you to actually plot those points in your book for that problem. And then the domain of this graph, I don't like how they did the less than or equal to here. The domain of this graph, again, is going to be 0 is less than x, which is less than 4.25. And I'm going to do this in interval notation. So I'm going to do parenthesis, comma, 4.25 would be my domain of my graph. All right, so here's how I'm going to graph this by hand. So I'm using, again, this column here, and on the y-axis, I'm using the volume. So on this particular graph, each one of these squares here, every 2 squares is 1. So this is 1, 2, 3, 4, 5. And it looks like every square here is 5. And so I'm going to plot 0.5, which is going to be right here. and then 37.5. So this is 25, 30, 35, 37.5 is right here. 1, 58.5, so 45, 50, 58.5 is going to be about right here. 1.5, 66 is going to be about right here. 263 is going to be about right here. 2.5, 52.5. 3, 37.5. 3.5, 21. And 4, 6. Okay, so that's what my graph looks like, and I can obviously tell it's not linear, and it might appear to be a quadratic, but it's not perfectly symmetrical like our quadratic graphs are. I can't really draw a line of symmetry down the graph, and so what I'm going to do is I'm going to go ahead and put this in Desmos so you can see a better picture of it. All right, so after typing this into Desmos, this is what I am showing. So again, there is a plus sign in the upper left-hand corner of Desmos that will help you put in this table. And you should see a graph like this. And so again, if I kind of sketch what I think is where the axis of symmetry would go, which it doesn't really have an axis of symmetry, you can see that this graph is not perfectly symmetrical, so it's definitely not a quadratic. But so this is a new type of graph. We're not used to seeing this graph. So this is going to actually be a cubic function. And the reason why I know that it's a cubic function is because it's showing the volume is equal to x times 11 minus 2x times 8.5 minus 2x is what I am graphing. And I have three factors. This is a factor, this is a factor, and this is a factor. And so since I have three factors, this is going to be called a cubic equation. And I am going to actually use Desmos to type this in and show you that it models this actual graph. Okay, so what I did was in Desmos, I typed in this equation, so you could go ahead and do that. And it basically went through every single point on our data. And so you can see that this is not a perfectly symmetrical parabola, so it is not a quadratic equation. Plus it has three factors, so it's not a quadratic equation. And what I'm going to do is I'm going to zoom out on this so you can see the whole entire graph. This is limiting our domain, and so we're limiting our domain from 0 to 4.25. This point right here is 4.25. And so I am only concerned with the graph from where x is greater than 0 and less than 4.25 for the box problem. But if I was going to look at this problem as an entirety, then I can zoom out and see the whole entire graph. All right, so this is what the graph looks like if I zoom out. I am showing, and there's some interesting things that we can see on this graph. We can see the zeros of this graph. So we have a 0 at 0, we have a 0 right here, and we have a 0 right here. And so we remember from our solving quadratic equations is if we have our factored form here, we can take our factors and we could set it equal to 0 and we can find our x-intercepts. So this factor right here, x equals 0, that is this x-intercept. If I want to take and solve 11 minus 2x and set it equal to 0, I get a negative 11 divided by 2, which is 5.5. That is this x-intercept, 5.5. And then if I set 8.5, I'll go up here. If I set 8.5 minus 2x equal to 0 and solve, I get 4.25. That is this x-intercept. So from this graph, I can see the x-intercepts, and the x-intercept are found by setting the factors equal to 0 and solving. Some other things that we can talk about on this graph are what we call the increasing and decreasing intervals. And so we're going to do that next. Okay, so this is, I've zoomed out on this graph. It's the same graph that we've been doing. And this is my cubic function plotted here. And what's interesting about this is not only can I see the 3 zeros right here, but I can also talk about the increasing, decreasing intervals. So this graph keeps going down to the left, and it keeps going up to the right. And so when I'm talking about the increasing, decreasing intervals, as I would take my mouse and trace this curve on Desmos, what's happening? So if I put my mouse, and I'm just going to use a different color here to show this. If I put my mouse right here and I trace, from here I'm going up. My y values get bigger and bigger and bigger until I get to this point. So right here my graph is increasing. Once I get to this point right here, now from here to here that I'm tracing in yellow, now my graph is decreasing. And then once I get to this point right here, and I'm tracing it, now my graph is increasing. So when I write my intervals from increasing to decreasing, normally what you're going to see happen is if I have the picture of the whole entire polynomial, I will normally start at negative infinity. So I'm going to start at negative infinity because on that using the x values here. So I'm using from negative infinity to the x value of this high maximum point here is 1.585. That is increasing. Then I will start at 1.585 and I go to this x coordinate, which is the minimum here, and that is 4.915, and that is decreasing. And then my last one here, I'm kind of running out of space here, so I'm going to kind of write sideways here. So my last one is going to start at 4.915. And it's going to keep going up forever and ever and ever. So this side of the graph is positive infinity, so it's going to go to positive infinity. And that is increasing. So my increasing intervals are from negative infinity to 1.585, union 4.915 to positive infinity. And my decreasing interval is 1.585 to 4.915. And so it's just basically you need to decide as you trace the graph, if you're going uphill, you're increasing. If you're going downhill, you're decreasing. And if you're going uphill, you're increasing. And this particular entire polynomial function had a domain of all reals from negative infinity to infinity. So that's why I started it at negative infinity and ended at positive infinity. With our particular problem, when we were doing the box problem, we were limiting our domain from 0 to 4.25. So I would started my first interval at 0, and I would have ended my last interval at 4.25 because that one was on a closed interval. So be careful of that when you do your homework. So good luck on your homework, and if you have questions, we will answer them tomorrow in class.